Right, so it's recording. I'm going to switch to the whiteboard. Okay, so here we are. Okay, so we were talking about how to train all these models, right? Whether it's linear regression, logistic regression, multi-layer perceptrons, or deep neural networks. So I'll kind of summarize today. I like to finish up this by putting all four types next to each other and then kind of pointing out some of the differences. Okay, so we'll go over that. But remember that at the end of the day, the intuition is that we're doing an optimization to learn the weights, right? And so we said something. So I'm still going to use the MSC example. MSC example here. Because it's the easiest to visualize and stop me. Oh yeah, sorry. Sorry about that. There we go. Thanks. All right. So we have the MSC example. So this, we covered before in the previous discussion, right? And remember that we said that we have two functions, which are the inference and loss, correct? Right? And then you can, to understand them a little bit better, you can think of them graphically. All right. So for the loss function, if we just look at MSC, then that means that there's an equation, a function that kind of looks like this. And because this is a quadratic, right, then it has a representation, yeah, which is this quadratic representation, a bowl shape, right? And what's important about this is that in this function, this governs a relationship between cost, which is denoted by J or the loss, and some parameter over here, right, given by the inference equation. So some value derived by the W's that we are trying to learn, right? And so our goal is intuitively to achieve that, right? The minimum of the function, right? But the problem is we don't want to select these randomly, right? So we know that when we have a function like this, and we have this is W x plus b, right? This is the inference function. Remember, this one plugs in there, right? And then we have this function, and then when we take what is called a derivative of this, right, we get information about this, right? And this piece of information tells us basically that this line, the tangent to the function, this is the result of doing the calculation, the derivative. But what's important about this is it tells us if we should go that way or that way. You guys see that? That's it. But that's, this is how we do this without having to do it random, right? We do it in a smart way so that we can find the solution, okay? And then the learning rate just means is the step size really big or is the step size really small, okay? So that kind of summarizes that. That's what we covered, okay? So we talked about the functions that we had, right? And today I'm just going to talk about a little bit of how the gradients are calculated. So the idea of calculating this, the derivative of this, right? So J, so you take the derivative of it in terms of some parameter, like W, right? So we're just going to do this example just to kind of illustrate how it works in TensorFlow. We didn't do this last week, I believe. And that's it, just to get a feel for that. All right. Another thing is you do have some reading. If that there's more to this, right? So I give this to you as reading. Let me go to here. I already have it. So I put a PDF here, right, in the STEM repo. Okay. So this is basically the course notes are here, pretty much a lot of what I say, except that this was written for TensorFlow 1. So don't learn TensorFlow 1, right? So just learn TensorFlow 2. Actually, TensorFlow 1 is being phased out almost, so certainly don't do that. But just click on this PDF, and basically you can read everything, chapters. These are my notes for the class. So it's got everything And some of these things you already know, like the arrays thing, right? What we did at the beginning of the semester with the linear algebra. I would recommend that you read chapter 2, right? This is just, again, I'm not going to quiz you on this, or it's not going to be on the exam. This is on your own. Read it if you have further questions. I go more in depth. It's got a lot of algorithms here, like support vector machines. I'm not going to cover that, right? There isn't enough time. Okay, but I go into all these algorithms, so you can look at the traditional, talks about optimization, the metrics, performance evaluation. Then it talks about data loading and pre-processing. So we looked at one-hot encoding, but there's a few other concepts you might want to take a look at. And then chapter 4, deep learning, which is actually what we're doing right now, right? So what I'm doing right now, for instance, I only explained the binary cross entropy. I didn't explain the multi-class cross entropy, but you can find the information here, okay? Don't read beyond chapter 4. Chapter 5 and all of that, we did not cover. Those are advanced topics, not from 365. Okay? Yeah, go ahead.
Where was that?
It's in the repo. So if you go to the GitHub repo, and then just look for STEM. There's a repo called STEM. When you click on that, you scroll down, and there's a link in here. Course notes, PDF, and you can just download it. Again, this is just more for you to we just don't have enough time, right, to continue going in this, right? But you can find a lot more description of the topics. Does this make sense, guys? Any questions? All right. So anyway, so that's that part. So let's do one example, about the derivatives here in TensorFlow. All right. So we're going to do the analytical solution. You guys are probably sharper at this math stuff, Luke, right, than me. So don't embarrass your teacher. All right, but I'll go over this example. We're going to do the analytical example, and then we're just going to implement this in TensorFlow. Okay. So basically, what we do is we're going to take the derivatives of this. So we have. And we will use literally TensorFlow's ability. So this just demonstrates that this is what TensorFlow was built to do, right? To calculate these parameters. So we're going to start with two variables, W1 and W2. Okay, so 3, right? These are the values. And then we're going to have a function. So the function looks like F. So 3W1 square plus 2W1 times W2. What does this represent? The loss function, right? But I'm not using an actual loss function. It's just some function. Got it? All right. And what we're going to do is illustrate the fact that the gradients are actually associated with the variables in TensorFlow, right? Whereas in calculus, like when you do the analytical thing, it's associated with the function itself, okay? And that may not be intuitive to you if you've seen this before, but just keep that in mind, right? The variables are what holds, so they're just evaluated to the derivative. So it's almost like if you have these values and you plug them into this function, you get some value. And then if you have the derivative of this function, you get another value, the result of it. You see that, like the plus, minus, and so on. Make sense? Okay, so that's the idea. All right, so then for this function, we can work it out. Work it out as, by plugging in those values, F would be 3, 5 square, right? Plus 2 to the 5 times 3, correct? And that should be 3 times 25 plus 30, basically, right? And that should give us 105. So this is the analytical solution to this, right? We just plugged in the values in the function. We'll do this in code in a second. Okay, so it gives us 105. Then over here now, the calculus thing, what that means is that it takes these derivatives of that function, right? With solving it through the analytical solution should be I'll write the function again, f equal 3w1 square plus 2w1 times w2, right? So then we're going to take, so now you take a derivative. So I'm going to say a, which is going to be the derivative of that function in terms of w1. You see that? Because you do it in terms of that parameter that you're looking at, right? Why? Because you're optimizing for that parameter. Do you guys see that? So remember that the value that you get for this parameter is the one that determines plus minus 0. That's it. Don't worry about anything else. You just want that mechanism, okay? So in this case, this is the partial derivative of f with regard to w1, right? So that should be then, let's see. So you guys are experts. So this is going to be, sorry. So this should be 6w1, correct? For the first part, w1. And then plus, what is the next part? 2w2? 2w2, right? Because it's the derivative in terms of w1. You see that? Don't worry if you don't know this, you know, that it's not important. What's important is this is the loss function j, and then you take the derivative of it. And what happens is you had this function, you had this function, and now you have that function. Do you see that? That's what TensorFlow is doing. That's it. And then for those values that we had before, where are they? W1 equal 5, W2 equal 3. What do they represent? They're the tensors, right? The values that you need to solve for. Okay, so now this becomes, the solution is 6W1 plus 2W2. Okay, we also then have to, for the other parameter, W2. You see that? See how, imagine if you have 52 billion parameters, you have to do all of this. You see that? You can't do this from scratch. You need these. This is where TensorFlow does all of this for you. Okay, so let's do the next one. So it's going to be derivative of the same f, the original one, but in terms of W2. All right, so you guys then can tell me here. In terms of W2, what is the value? The first one becomes what? 0. 0, right? Yes? Right? And 0. And then the next one becomes what? 2W1 from this one, right? Because you're deriving in terms of W2. Yeah, so it should be 2W1. So I'll get rid of this 0 here. Oops. And again, how do you know this? Calculus has these rules, right? And you have these solvers. But what's important is you derive in terms of one weight and the other weight, right? And this is how you figure out then that plus, minus, or 0 that's going to update the weights. Does that make sense? That's exactly what's happening behind the scenes. All right. So now that we have the two functions, so TensorFlow has solved this for you, right? And now what you do is you just plug in those values, right? So in theory, this should be what? This should be 5, correct? Plus 2, 3. So that's going to be 36. Do you see that? So the value itself is what you get because you had, and you have the values, the tensors, right? And then you have an original function, the loss function. And then as you're doing stochastic gradient descent, you're calculating these derivatives. So you go from the original function to these new functions, okay? And then now in these new functions, you evaluate the original values, W1 and W2. So we did 5 and 3 here. That gave us 36 for W1, right? For W1. So this would be for W1, right? Because that's in terms of W1, I should say. And then for the next one is going to be what? 2 times W1, which is 5. So that's going to be 10. Those are the two values that we get. And that's what TensorFlow is going to give us. Got it? Any questions? So let's go over the code. So we've done this in the analytical solution. Now let's take a look at this. We're going to write we're just going to play with the gradient, the gradients calculation in TensorFlow, one of the ones that are available. Okay. So we're going to write this code. I've already installed some of these libraries, so you guys will probably need to install them. You can just copy them. So I'll just copy the code from the GitHub. So I'm going to go ahead here. Okay. I'm already in the environment. So I'm going to start the Jupyter Notebook. Now, this is not just this, this is not stochastic gradient descent. This is just what, stochastic gradient descent relies on this to be able to update the weights. Okay. So we're going to start a new Python script here, Python 3. It's not seen. Oh, there it is. Okay. So we're going to call this gradient calculation. And again, this is just to illustrate what's going on behind the scenes. Okay. So I have code here. Gradients, so you can just get it from there. The code is available to you. So basically, I'm going to copy some of the libraries. And you'll see some of the mechanisms that are available in TensorFlow. So here I'm using NumPy, TensorFlow, and Matplotlib just to plot things a little bit, right? So run that, load the libraries. Like I said, this will break for you probably because I already installed that MPL toolkits. So it should just be pip install MPL toolkits, I would think. Let me know if that doesn't work. And also pip install Matplotlib. And the other two you should have. Remember, this is in the GitHub, so you can just copy it from there. Any questions while this is going on? So I'm just doing that. Remember, this was the function basically that I just wrote by hand. It's literally the exact same function. So I just made it into like an actual function in Python. Notice it's the W1 squared times 3 plus 2 times W1 times W2. That's it, right? So that's the function. All right, it's taking a while. So if you I'm going to go to the whiteboard while it's still loading. So you can see here, we need these two values, 5 and 3, and we have this function here, right? That's the one that I just added the code for. So then the first thing we might want to do is just plug in W1 and W2, and we should get 105. Okay, we should get 105. Let's try to do that. All right, it finished. Good. So no errors. All right, so now I'm going to hit run. I've loaded the function. Okay. now we can take a look at the, let's see, I'll create some ranges later, but let's just make the call. Right, so if you notice, that's the function, and I provide the two values 5 and 3, right? Oops, 5 and 3. Okay, so this should give us 105 if I run it, and there it is. We get 105. That's it. All right, now just like you can do the analytical solution by hand, as I showed you, pretty much you can do it via TensorFlow. The only thing is, if you've ever done a lot of this analytical solution by hand, then you expect somehow to get another function, and that doesn't happen in TensorFlow. TensorFlow does things behind the scenes. What it gives you is the values, right? That's it. And so that's sometimes I have found that over the years, it's not intuitive how that works, but that's how it works. Okay, because that's really all it cares about. So it's not a module for calculating derivatives, it's a module for optimization of neural networks. Okay, we're also going to need some ranges for the plotting, so I might as well copy them before I forget. So I'll copy this. Okay, so I created some ranges from 0 to 10 for the X and the X called X1 and X2, and they're for the W1 and the W2. All right, so just so that we can plot things, have some values. So you can see here, generated that data. Okay. Then we can go to the here. You can plot this. All right, this is just, I'm just going to copy this code just to plot given that function, right? Given that function, what that function kind of looks like. Okay. This is the function, not the derivative of the function, but the function itself, okay? You can see that, so that's kind of what it looks like. So the analogy is that you're thinking of, if you were thinking of the quadratic, right? So if we go back to the whiteboard over here, I think we started, right? Remember this, guys? Right, so the quadratic just looked like this bowl shape, yeah? That x2, and then we take the derivative of it and find out for the values where they fall in the tangent of it, right? So what we're doing here is we're just plotting that function kind of in the same sense, okay? Luke is going to give us a solution of when you take the derivative of it, and he's going to earn some points for it. All right, so yeah, so that's kind of the idea, okay? So let's go back here to the code so that underscores that. Right, so now we have this function, and now we're getting close to the point where we want to take, just like I did the analytical solution, we want to see this feature of TensorFlow that does this as well. And this is called calculating the gradients. It's really, I think it's really important that you guys are aware of what this is, so that you don't get confused when people start talking about the gradients and whatever. You should have a sense of what they're doing and the importance of it. Oh, there's another plot actually called the contour plot, which is actually better for visualizing, because here you can't really tell where 105 falls, right? It's a little bit difficult to know, where's 105. So there's you can also plot what is called a contour plot, which is this one, which is also provided for you guys. So I'm going to hit run on that one. And so seeing 105 for 5 and 3 should be a little bit easier, right? So 5, 3, kind of here, right? In this area, and this area, according to the color grade, yeah, is 105. Do you guys see that? So this is like a light blue type of a thing. So light blue. It's just another way of visualizing things. But it's because 105 is that 3 and 5. All right. Hit save. Okay, then, okay, so I plotted that, okay? Now we are actually going to proceed to calculate the gradients, which are just fancy terms for saying we're doing some kind of a derivative, right? And I kind of just want to demystify that. So here I'm going to add just a little title. Markdown, hit run. All right, so now calculating the gradients. Now, as I said, it's not so intuitive in the beginning how TensorFlow has implemented this, because really what you do is you create the variables, right? So if you notice, now I'm going to create that W1 and that W2. So I'm going to grab the other one. Okay. And if you notice, they are now tensors, right? They are TensorFlow or TF.variables tensors of values 5 and 3. Does that make sense, guys? So you can imagine there's a computational graph that holds these two tensors, right? And they're tied to an equation. That equation you calculate the derivative of, and then these values run through that one to get the results that we should have gotten with the analytical solution. So I'm going to hit run here, right? And I've created basically the variables are initialized. All right, then I'm going to go over here. And now comes this thing that TensorFlow has invented called the gradient tape, which I literally think is like they thought of a tape and now they're sticking things on that tape. You guys see what I'm saying? Like it's literally called that. As you can see, the gradient tape. So with tf.gradient tape as tape, and basically what that means is that they're sticking things to that whenever they want to do this kind of thing. All right, so they're sticking here what? Notice the function, right? So you have z, and c now is starting to represent a graph, a computational graph. Got it? And what is a computational graph? It's basically what? Two tensors, which are W1 and W2. You see that? In some relationship. And the relationship is what? The equation itself, right? F. And that is defined, if you remember, by this one. All right. So all of this becomes like a computational graph in TensorFlow. Okay. So if we go back to the whiteboard, this is actually how everything was explained back in the day. So like when you start reading through that book, the course notes, chapters 1 through 4, you'll see that a lot of the discussion is the computational graph, which is still there, but it's just not mentioned so much anymore. So if I have my notes here, somewhere. So it's like you've created these tensors, W1 equal 5, that's a tensor, and W2 equal 3, that's a tensor. But now TensorFlow, right? So you need to create a computational graph. So there's an operation 2, right? Square, basically, of 2. Let's say, actually, that should be one. The operation is squared. Okay. And then you have another operation, which is multiplication, right? Times 3. You see that? So you start to lay out this computational graph in memory. That's what TensorFlow is doing. And that's why it's called TensorFlow, right? So all of this is happening. Here you have W1 also with a operation, or you can say the result of this, actually. The result of this, right, gets connected to the rest. And so you start creating this entire computational graph that captures the function, okay? So that's how it works. Any questions on this? Does this make sense, guys? Yeah, so it's a graph that represents either the tensors or the operations on the tensors. That's it. Okay? And then that is stored in memory somewhere. And then when it comes time to calculate the gradients, it just doesn't, right? For that graph, it calculates the gradients. It just does it on its own. But this is how it's set up. Any questions on this idea? Clear? All right, great. All right, so now let's finish up that script. So I'm going to go back to the code over here. Okay. All right, so we've got the gradient tape. So if you notice, we've said TF gradient tape as tape. We tied the, and actually I'm going to do this in the next line. So we've tied now the two tensors to the function, and we can reference everything by Z. That's the great thing about it. C becomes like the thing that we can grab, and it refers to the entire computational graph. Okay, so I'm going to hit run on that one. And then now I can add this one here. So if we look back, if you notice what happens here, now you just say tape. Tape is the thing that holds everything together in this sense. And you just tell it gradient, dot gradient. At that moment, you're telling it to take the derivative of C in terms of W1 and W2. Got it? So now you have the results in gradients themselves, right? So that should give us a couple, should give us a couple of values. Let's do run. Now I'm going to just do gradient. Gradient, hit run, run. And it gave me an error. Oh, yeah. Okay. There we go. Did it work? When we did the analytical solution, right? It should have given us 36 and 10. Right? So if I go back to the whiteboard, we did it somewhere here. So if you notice 36 and 10. You guys see that? Yeah. And now if we go to here, 36 and 10. There we go. That's it. But so that's it. I mean, that's literally all I wanted to show you. You don't even use gradient tape to do the actual gradients. You just say step or, whatever, right? Atom optimizer step. But they created this gradient tape so that you can somehow maybe sometimes play with the graph itself and look at it. At the end of the day, what my point is, if you've done this a lot analytically, you probably wanted to see the function, but that's not how it works. Instead, everything is tensors and the value of the tensors after the gradient has been calculated. Questions? And now these are the values that, fall into this idea. If I go over here, right back to the whiteboard to conclude, so now they represent this, right? So the indication of this tangent on the loss function, and now you can update the weights because if it's a positive, negative, or zero. Got it? And I'll do one last example that concludes the code actually. So let me just look at it. I think, yeah, that was it, right? So we did it. You can just copy it from the GitHub and run it on your own, play with it. But I want to do another example. So a neural net, usually the intuition, right, that we look at in a neural net is that, we've said something like, it looks like this, right? It has multiple local minima, global minima. A lot of work goes into this idea. A lot of people try to smooth these. They have techniques where they may actually make them smoother, and that intuitively makes it better, right? But what we're doing is, if you're here, let's say we do one more. Yeah, like that. And you're kind of like there, right? So you want to figure out, okay, I need to go in that direction. That's what that accomplishes. And hopefully you read the paper, right? Remember, I provided a 3-page paper for stochastic gradient descent. That's in the GitHub. Don't forget to read that one. That's from the authors themselves. So you can also, but this is the mechanism that does it. So this was not possible. This theory has been around. It was invented in 86, right? But it wasn't until we had enough computing power that a lot of these things could be done. All right. And so this PyTorch, TensorFlow, and all those tools that do deep learning basically do this. Okay, do these derivatives as we saw, but for billions of parameters. Efficient. Any questions, guys? Does this make sense? All right, so that's kind of it as far as that idea. All right, and then all I'm going to do now is kind of wrap up everything. I'm going to contrast, you know, the linear regression, logistic regression, kind of summarize their cost functions, right? So you should remember the cost functions that we talked about. How many cost functions did we have in general for machine learning? So that's like an exam type question. What are the loss functions? MSE. What's the other one? Cross entropy. But cross entropy has two variations, binary cross entropy and multi-class cross entropy. Remember, if you want to learn about multi-class cross entropy, just read the PDF. It's right there. Okay. I won't ask. I won't go into such depth, but a lot of the additional things that I'm skipping are there. All right, so we are done with this part. And I didn't hear any questions, so I assume you guys got it. Okay. All right. All right, so that's the fundamentals part. We got really fundamental. All right, so linear regression. Like I said, now I'm just, for the rest of the class today, I'm summarizing and just wrapping up neural networks, actually. So maybe you're sad that, you know, this is the last neural networks discussion. All right, but yeah. So linear regression, if you remember, so just kind of summarize all these models, I'll kind of list them out, right? So believe it or not, you know, like when I was learning about this stuff, they would teach me, you know, here's linear regression. And then over here is logistic regression. And then over there is neural networks. And no connection was made between all of them. You know what I mean? And they're actually connected. They're almost like, if you've ever seen that cartoon of, you see like a caveman, cavewoman, right? And then you see like Renaissance and then modern person. You know how it evolves? It's almost the exact same idea, where you could literally go linear perceptron, linear regression, logistic, and so on. Got it? You're adding on to the things, and hopefully that's obvious to you. I don't know if it is, but hopefully it is. So I'll try my best to do that today, right? To convey that they're actually quite linked, and that a linear regression can be thought of as a neural network. Logistic regression can be thought of as a neural network. Perceptron is thought of as a neural network. Multi-layer perceptron all the way to deep learning. All can be thought of as neural networks. So they are, you know, the ones that fall within this that we are discussing: perceptron, linear regression, logistic regression. Also in that chapter 4, I have a section which I call From Linear Regression to Logistic Regression. I would strongly recommend that you read through that. It has more details with a very specific example of housing prices, of how individual linear regressions can become, you know, the logistic regression classifier. So you have perceptron, linear regression, logistic regression, MLP, which when I use the term MLP, what do I mean? I mean an input, an output, and a hidden layer in between. I always kind of mean that. And then when I mean deep learning, I kind of mean 2 hidden layers or more, okay? And then, as you know, there are advanced algorithms. So let's kind of, and we saw one of them, right? CNN. Yes, you guys, and I kind of explained that with the filter, Lena, right? We went over that, I believe. So that's CNNs. A few other advanced algorithms that we did not cover are RNNs. This is the sequential one, and of course, the transformer. Okay, these are the extremely deep pre-trained models, but they're still neural networks. They're still building on top of DL. They just have additional things going on. Okay, they're very deep. You saw like that ResNet. If you're using that for the SciFar 10 competition, I believe it has 150 convolutional layers, not just simple layers, but convolutional layers. They use something called residuals. which was not in the original code I gave you guys. Residuals actually, in my opinion, I'm finding out, is actually the thing that has made deep, really, really deep neural networks possible. And that's the scary thing of AI, right? Because they can be really deep now. And so they can do lots of things like memory possibly, and not just inference. All right, but anyway, so we got as far as here and a little bit of this intuition, but obviously we're not going to cover these two topics. They're just too complex. Okay, now they all come from the perceptron, and it's always good to think of them in terms of linear regression. Okay, any questions about this? Nope. All right, so this is NNs. Okay, NNs. So now we're just going to think of linear regression, right? So you guys know linear regression, right? It is like this. Okay, so you have some data, and remember that your goal is to fit a line through the data, right? That's kind of the idea. Now, one important thing is the intuition. I want to give you this intuition of how do you calculate the best line, okay, the best line. So that's kind of what I'm going to try to do as best as I can. So I'm going to do an example here, and I've got some data. The samples, and then I'm going to fit two lines, which I'm going to call A and B. You guys see that? So there are actually two lines here. So the dots are the real data, and the A and the B are what? The neural network or the function that you learn. What's important there, you learn weights, right? You learn the weights that put everything together. Okay, so once you have this, then you have X, right? This is X, and then this is, let's say Y or whatever the value is. But you say for this X, right? For this X, and I can use different colors here. So let's see. So for this X, whatever it is, X something, let's call it XI, right? The real value is this one, right? So that's real. Yes. The predicted value for the B model is this one. Do you see how what I mean by that? So this is the B predicted. So maybe I'll say real Y, BY, right? And if I keep going up, right? So this is probably like that, actually. So if I keep going up, straight line. You see that? That is AY. Yes? AY? Okay. So you see that's the intuition that we have, that we have the real value, and then we have two models. And one predicted this value, one predicted this value. So when you say the optimization of MSE, right, what are you saying? So you say something like the sum, right? So the sum divided by n of y hat minus, real squared, right? That's what we say. So what that means is, I'll use a different color here. Orange. Is that the differences here, if you look, is this is the real, right? So so the real is this value here, right? And then y here is the predicted. So it can be either y hat A or y hat B. Got it? So then what are we doing? We're taking the difference squared. Oh, that's a color that's probably not good for them. Okay. So then you've got that distance. You see that? Which is the distance between the real and the predicted of B. But you also have, and I'll change to another color. Where does this one end? You see that? So it's this distance and that distance, right? So intuitively, then we can say that we have, now imagine we have many more, right? So I'll do one more. Let's say I have the real value for this one is like here, right? So then the predicted is like right there. So the distance is that one for the light blue. And then I need the distance for the dark blue, which would be what? Probably there. Yeah. Like that. Do you guys see that? So basically what we're trying to do in the minimization is what? Minimize the sum of the differences of all the points. Got it? And then the one that minimizes that gets the best, is the best weights, right? It's the closest fit. So here we could say sum of A versus the sum B, right? Where this is made up of all the differences. This is made up of all the differences. So you have, you know, for A, D1, D2, all the way to Dn. And then here, D1B, right? D2B and DNB. You guys see that? See what I'm doing? So it's the sum of all these dark blue and the sum of all these light blue, right? And then you want the one that minimizes it. So of these, so what would the symbol be here? Which one would you expect to have a greater sum? Is it this, that, or this? Which one of these for this example? Of these three? Which one? Oh, A. Oh, you mean the first? You meant the first one? Yeah. This one, right? So then get rid of the other ones. Exactly. So you can get rid of this one. So basically, the sum of the A's is going to be greater than the sum of the B's. You see that? Intuitively, that's what this equation means, right? That, you know, you're selecting, and it makes sense, right? Because the B red line, the B straight line here is a better fit to the data. You get it intuitively? That's it. All right, so hopefully that made sense. I can't do this for every single loss, but usually this is done for MSC. We did do it for the log, right? We already went over this in the video for the log, the cross entropy. So I gave you the idea of 0 or 1 because you're trying to predict the probability. I only did it for the binary case also. Keep that in mind. Okay. Any questions about this, guys? All right, pretty easy, right? All right, so we're just going to conclude then with the comparison of all the models, and I kind of list out like the characteristics of them. So definitely learn this because this might be like on the exam. But just a comparison of what are the differences. We've gone over all of this. Okay. There it is. All right, so we're going to now contrast, you know, most of these at least. We've got the perceptron, linear regression, logistic regression, multi-layer perceptron, and deep learning. I'm going to skip CNNs as they are more of an advanced topic. So, but we're just going to compare these. So perceptron, right? And then linear regression. Okay, so my intention here is to show you like they're kind of the same thing, but they just, you know, have differences. Logistic regression, and also we have to draw the networks. Okay, that's the other thing. Logistic regression. MLP for multi-layer perceptron, and deep learning DL. Okay, so these are the five, I guess, and they kind of evolve in that direction. They evolve in that direction. So we start with the perceptron. So we had in the perceptron no hidden layers, and we had a sigmoid, right? So we had something like Z equal the weights times the X values plus B. And then we had sigmoid, you remember, of Z, right? We have something like that, right? And we went over all that code in great detail, okay? If I have time towards the very end of the semester, I might do the MLP from scratch, but it's only if I get through the other topics first. Okay, so we went over definitely perceptron, and that gave us an idea of the update, right? The update of things. Then linear regression, we want to think of it. Again, we're predicting, so this predicts a sigmoid, so a type of 0 to 1, correct? So 0 to 1. Okay. Linear regression, WX plus B. What is the loss function here? Or the optimization, or whatever you want to call it, cost function. MSE, right? Mean squared error. Okay. What is the output of linear regression? Does it predict? What's the activation in the last layer of linear regression? Does it have a function or something? What's the output? They're the same question, actually. It predicts real valued numbers, right? So you basically any value between minus infinity and infinity. Here, we constrained it to 0 and 1, right? What is the loss function of perceptron? It had that weird rule that we saw in code, remember? And we actually played with it. Don't forget. Is this clear, guys? Does this make sense? Yeah. So remember, what do I mean by this? This can predict 78 or age 13 or age, 23, right? That's what that means. Whereas this one can only predict 0 to 1. How do you achieve that? Notice the difference. They're basically the same equation, aren't they? Except this is constrained by going into another function like this sigmoid that only produces 0 to 1, right? And we talked about those activation functions. Does that make sense? But whereas this one does not. Now, the perceptron goes through an activation function. Does that mean that it can approximate nonlinearities, or is it still linear? We talked about this. What is it that allows you to create nonlinearities? Not just activations. You need hidden layers. Remember, don't forget that. And it's in the GitHub, right? I provided some discussion. If you don't remember, it's in the neural nets section, I believe. Let's go over here. Get this, because I might ask this as a question. Neural nets here, right? So this was the question of question and answer of what is it that actually creates the nonlinearities? So but is just having now another question. What if you have 3 hidden layers but no activations? You see, you need both. That's the whole point. So perceptron gives you activations but no hidden layers. No, you can have a neural network with 3 hidden layers, but if there are no activations, it's still linear. So you need both of them. Okay, but just now remember, once you have even just one hidden layer with activations, let's say 2, and it's a universal function approximator. In theory, it can approximate, let's say, a lot. Okay, which is what makes them what makes AI scary, because it can literally do anything. I mean, if you think about it, if it can approximate any function, that means it can deduce anything, right? All right. So anyway, so let's go back to whiteboard and wrap up. Like I said, these are more like exam questions. All right, so logistic regression. So we did this, right? MSC. Now logistic regression. This might be a tough one. So does that still look like W X plus B? And does that also look like a Z going and then Y equal C going through a function? Right? It looks like that. Now this does not update like the perceptron anymore, right? Now this will use a loss function. So now you can calculate derivatives and all of that, like we just saw, gradient descent. Which one can you use? You can use cross entropy. Okay. So logistic regression, is it linear or nonlinear? Or is it a neural network? I mean, all of these are, it's the way that you think about it, right? They're all the same equation, W's and X's, right? But you have to think about, one way of saying this probably that's better is, does it solve problems like you want it to solve problems? Complex problems like XOR, right? We saw that only neural networks could do that. Remember that? We did the XOR. Did logistic regression solve XOR? It did not. Why? Because it's still linear. But it has an activation. So what's the problem? What does the network of logistic regression look like? If you have, let's draw it, right? So at this point, it helps to draw all these things. So let's say that we're doing iris. So logistic regression can do classification, right? This F then could be what? Any activation function, okay? So if you're doing classification, what makes sense here? For iris, let's say, just to give it a little bit more context, right? So iris is how many inputs? 4, right? How many outputs in iris? 3. So it's a classification problem, correct? Multi-class. So what activation function? So why softmax? It adds up to 1, right? So it helps out a little bit more. So that kind of makes sense here to start thinking about softmax. But do you guys see the relationship? Like, it's all kind of related, right? There's this. Now, this network, how do you draw cross entropy here? Sorry, logistic, I keep saying that. Logistic regression. What does it look like? Anything else? Or just the connections, right? So remember, so if I ask you to draw these out, believe it or not, and check the chapter 4 in the book, I drew these diagrams in there for all of these, so you can check it out if you want.
Just a question. If you use those that function,
it's essentially the perceptron, yes. Yeah, essentially. Except there is no softmax here, whereas this would have 3, this only had 1, because it was from 0 to 1. Because it's almost like you were saying, if this value was less than 0.5 or more than 0.5.
Yeah.
Yeah, that was the only thing. So this basically still gave you a value between 0 and 1, but you were just saying, like, is it less than or more than? The step function, okay, from perceptron.
Yeah.
In the output? Maybe. You're talking about like getting like this, right? That's what you mean. If they're individual, yes, actually, because it can happen. But I think you know what, it depends on this, on the real values. If you had this, that mechanism would approximate that. Because really what you need is a machine that creates zeros or ones. Right? Do you see what I'm saying? Where if you so I would think, to answer like this. If I have a machine that produces 0 or 1 here, 0 or 1 here, 0 or 1 here, right? It can predict those. And I train it with this, like 1, 1, 0, then why not produce 1, 1, 0? It's going to learn that. Now, if I give it that, then the machinery, as it's learning the weights, it's learning to mimic it, to replicate it. So what the functions do is like this clever thing where you say, I want it to produce ones and zeros, right? And you can have multiple of them or just one. And that's why the softmax is kind of nice, because then the softmax allows you to just select one thing. It's like a little bit more pronounced in the separation. Did I answer your question? Yes. Yeah. All right. Yeah. Okay. Does this make sense, guys? Any other questions? But yeah, that's a good one. So yeah, so we create these models and then we use activations to kind of force what it outputs, right? Force it. All right, so we did logistic regression. We did this. Remember, we're using a loss function here, cross entropy. We kind of add this softmax idea. Okay. And these can be, so if without the softmax, what's going to happen? We can get still values, right? Between 0 and 1, right? But they just don't add up to 1. So this could end up being like 0.8. This could be end up 0.7, 0.4. They do not add up to 1, right? But that's what we can expect to get. All right, given whatever we have given it here, right? So that's literally, it learns to mimic, basically. All right, multi-layer perceptron MLP. So guys, you guys can help me out to do this one. So well, let's start with the equation. So that's WX plus B. Okay. And then how do you write the rest of an MLP here? What makes it different from the previous ones in terms of equations? This would be hidden one, right? And then that hidden one becomes what? The input to the next layer, right? So then I'm going to do, now, once I get this hidden one, now I can write this in a couple of ways, but one thing I shouldn't forget is that you need both the layers and the activation functions. Because remember, if I just draw like that, right? And then I'm going to do H2, which will be, oh, this should be 1. And I do W2, what value goes here? H1, very good, because it's the next layer, right? So that's exactly what's happening, like literally. And so this is H1B, and then I can keep stacking layers, right? So I can keep stacking layers. So I'm going to do H3, W3. Notice that the weights are different. There are neural networks where they try to share weights and stuff like that. You know, all kinds of things are tried. Now here the input is H2 because it's the previous layer they're connecting plus B. These should be the independent B's as well. And then the last one would be the outputs, which would be W4, let's say, H3 plus B. If I gave you this on the exam and I ask you, is this a linear or non-linear model? Huh? You would say what? Linear, yes, a linear model. You see that? Because it's missing the activations. So, but in perceptron, we had the activation. So then you might be confused to think that it's nonlinear, but it's not, because you need, or it can't solve things with non-linearities because it needs both the hidden layers and the activation, right? And that's what I put in the blog post on the README. All right, so now what I'm missing here is the F, right? So I didn't leave much room for that. So I'm just going to do it like this. So F, F, F. These are the activation functions, right? We saw how to code this in TensorFlow. What were they? Sigmoid, tangent, ReLU, leaky ReLU, and then the softmax usually for the N if you have like a classification problem. Got it? All right. Any questions about this idea? All right, so that's a deep learning. What's the loss function for this one? Cross entropy, right? Cross entropy. And just keep in mind, and we saw this in TensorFlow itself, you select either binary cross entropy or categorical or multi-class cross entropy, right? One of those. So it's pretty easy in Keras, because you literally all you have to do is just say the word. But you can write the equations if you want. Just remember, I think I've told you this before, it's just not recommended. Oh, actually, this, I was thinking of the deep learning. This is wrong. This should be DL, right? Because it's got how many layers? 2 hidden layers. You guys see that? And so I made a mistake actually there. So let me just rewrite this. So this one will be the MLP, as I usually define it, or has been traditionally how I learned to define it. Very difficult to get me to change now. But so then this would be W1X plus B. So we just have one hidden layer, right? Start with the original X. And then here, then we can say Y equal F W2 H1 plus got it? So it just implies that there's one hidden layer. Okay, so if we're going to draw these in a sec, just to kind of give you the last component of it, as sometimes you might see the neural networks drawn, sometimes you might see it in functions, etc. And I'm trying to keep this as close as possible to the code. Any questions about this, guys? And what is the loss function of MLP? Cross entropy, once again, which is that idea of the log, right? So we went over that on Thursday. So check out the video if you don't remember. Also, it's described in great detail in the notes. So just read through it as well. Okay. All right. Yeah. So that's basically, so I'm not hearing any questions. So let's just draw the networks then, so that we have a kind of a summary. I don't have all of them here. So let's see. We have, yeah, so the original perceptron kind of looked like this. It was, I'm just going to use a few neurons, ... And then we had a function from 0 to 1 that's connected, right? That's the original perceptron, linear regression. I'm just focusing on the layers here, right? That's kind of the intuition. So linear regression, how many layers? How many outputs for a linear regression? How many outputs do you have in linear regression? One? Just one? Could you have a linear regression of more than one output? Yes. right? So that's possible actually. So you could have more, but in general, people think of linear regression as just one output, but there is multiple input, multiple output linear regression as well. All right. What I found about those models is that they're hard to train because one goes up, the other one goes down. It's like you maximize one error and then the other one flips. So that's my intuition with them anyway. But this is the network for linear regression. Do you guys see that? No hidden layers. Now, can you use a neural network to produce linear regression? Or is linear regression this network? What do you think? What defines linear regression is, I guess, what I'm getting at. So could I have a linear regression with one hidden layer? No? You did this in the homework. The Weka linear regression, do you guys remember? You could use an MLP for it. Why? Because you can a neural network can do whatever it wants, right? That's so I can have a neural network like this. Why not? And one or two. What's a linear regression? You see what I'm saying or no? Do you guys have a doubt? What's a linear regression? Predicting, let's say that I'm predicting heat, right? What's the temperature here right now? Probably 70 or something. 72. Tomorrow, 75. That's a regression. You see that? That the fact that I predicted 75. What if I predict is it going to be hot tomorrow? Yes or no? That's classification. But a regression is just predicting a value. And I can have multiple inputs, multiple outputs, however many layers. I can use a really deep neural network. Doesn't matter. So a linear regression does not mean the network simplicity. It means that this output is a real valued number, not a class. That's linear regression. What loss function do I use if I have several hidden layers in here for a regression problem? Do I use cross entropy or MSE? Very good. Because it's just a predicted and they're real. What the network has. Do you guys see that? Yeah, so I'm working on a problem right now. And I know this because I'm working on this problem. It's got 6 inputs, 6 outputs, where the outputs are things like it's the Gary works, the steel works. So it's something like the steam and the heat, and you know how they produce steel, right? So you measure like how hot it is, and I don't know, stuff like that. I forget what it is. But it's 6 inputs, 6 outputs. How did we solve this? We actually did a linear model plus a nonlinear model. So it's 2 models working together, right? And so you see that's some architecture, right? You know, and well, you can try a linear model. So it's like an f that's a linear function plus another f that's a nonlinear with however many layers you want. What matters is the output values. Got it? Questions about that? Yeah, so any architecture can. So this kind of was like a trick question, right? But what's important is here. So All right, logistic regression. Let's see logistic. And I ask you, just draw the network for that one. So in conclusion, for linear regression, right? For regression in general. So there's actually, I should say, for regression versus linear regression, right? So for regression problem, so maybe maybe this is where I confused you guys. So I should make a distinction between regression and linear regression, okay? Because nonlinear regression. Okay. All right. So definitely, I think I should have stressed that. All right. What about for logistic regression? What is the neural network that you guys would draw for this? For the iris data set? What else? For logistic regression? No, right? And we kind of defined that this is a linear model, correct? There could be a softmax or something, but it kind of looks like this. Okay. Questions? And let's do multi-layer perceptron. So I'm going to move over here, MLP. Yes, please. For the logistic regression, you would use something like a softmax for classification to get values between 0 and 1. Is that what you're asking?
Yeah.
Mhm.
Which is not application.
Yeah, so in a regression, and again, so I probably confused the term linear regression and just regression, right? So I want to stress really from regression, linear regression and nonlinear regression. Okay. But yeah, so your question is, in regression, is there an activation function here? There isn't. Is that your question?
In linear regression, there is no activation function.
In regression in general. In regression in general. Because linear, think of it as linear. And then nonlinear, you can have a neural network in there. But logistic has an activation. Yes. That's right. Yes. Yes. So if it's a sigmoid, what are the values from 0 to 1, correct? This no logist. Oh, I don't know. That's the name just comes from. I see where you're. So you're thinking because it's called logistic regression that it's behaving like. That's not my fault. That's just traditionally where it comes from. Yes, that's a good question, actually. Yes, exactly right. So I think it just comes from the fact, from this fact, in my opinion, that linear regression or regression, and then logistic means that you take a regression and you add this. This is sometimes called the logits, actually. You know what I mean? And so that's where that is. It's like they're saying it's almost like a regression, but it's a logistic regression because now we're constraining it to just 0 and 1. Yeah, but that's a good question, actually. This one is not meant to be an infinity to infinity. Only the actual regression one, which could be, and I should have said this more clearly, linear and nonlinear, because it could be a neural network. Questions or did you guys get confused? Or is it clear? It's clear, yeah. So that's it, a thing with the names, but yeah, logistic regression is basically a classification. I would say that the logistic just is that, taking a regression, but now constraining it to produce zeros and ones. Whereas in regression, whenever you talk about that, you're talking about minus infinity to infinity. Right? And as far as the architecture, then if there's like this, linear regression. So you guys were probably right that if you see linear regression, you should draw it like this. And if it says nonlinear regression, it could be a neural network. Any other questions? Clear? All right, hopefully. All right. So yeah, so what I'm trying to do, honestly, is I'm trying to like take just the original regression and put like the things, right? Put a activation, put layers, and this is how neural networks that work. If you look at CNNs, they do have a they do have a fully connected layer, but they have convolutions, they have residuals, norm. So it all starts from like this idea of regression that you start adding onto it. Okay. Questions? Nope. All right. So let's do the MLP. I think we were doing this one. Yeah. MLP, multi-layer perceptron. This implies one hidden layer. So if you draw it, right, that's what that means. Multi-layer perceptron. And then I think I'm doing iris here. So what are the activations? So this is the input. And just imagine these are connected. Fully connected. So what are the activations here? And this is a classification problem for MLP. But if I don't put any activations here, what does that mean? It will learn to produce whatever is the real vector. So if the real vector is 25, 33, it is effectively a regression. Yeah? Okay. So that's what makes the regression. All right, so what's the activation here that you can use? In general, ReLU, very good, perfect. ReLU, right? So we've learned that ReLUs work, or leaky ReLUs. There's one called GeLU now. All right, and then this one, if it's a classification of iris, softmax, which is just make zeros and ones, but they add up to one. So it's an extension of sigmoid. Now, okay, any questions on this one? Remember that in general, they don't produce like a 0 or a 1, right? What do they produce? Like 0.005 and 0.90 or 0.98. So when you select the class, you do the argmax, right? So which basically gives you the index of the highest value in the probability. Okay. All right, let's do a deep learning algorithm. DL. So of 3 hidden layers. So that would be an input, 1, 2, 3. Oops. For some reason, they're getting smaller. All right, so this is input, output, hidden 1, hidden 2, hidden 3. They're all fully connected. Activations here, ReLU's probably softmax if it's classification. Again, this DL, if you leave this like with nothing, it's effectively a regression. So it can learn any number that you give it. One recommendation, as always, is that you normalize the data, right? So don't forget that. All right, so yeah, so that's kind of it. I mean, hopefully I didn't confuse you there. That's it. So usually this is how I end this, just kind of showing this contrast of the functions. And that's neural networks for this semester. Right, so that's a lot of the theory. So we covered it in about a week, right? So a couple of lectures. And then what you have left is your Keras code, right, for the challenge, right? You know, you can play with it. And so, yeah, think a little bit more about these ideas. And if you have any questions, just let me know. But yeah, if anything, the clarification I do want to make is that regression thing where there's linear and nonlinear, and then regression just really means that the output is not classes, but can be real valued numbers. It can be 80 real valued numbers, right? An image, like a generative model that generates an image that is 28 by 28, where the pixels are from 0 to 255. You could think of it as a regression if you want to think of it that way. Okay. All right. Yeah. So that's kind of it for me. We can stop here for today. And please, on Thursday, we'll just, you guys will do your presentations. right? Your short presentations, kind of competition, kind of a feel. And then if we, for some reason, end early, then plan to work on the second part, the image part. Right? And are there any questions about the competition? You guys are working on this, I assume? Right? You're not going to start like tomorrow. All right. All right. So good luck, and I'll bring the trophy for the winner. All right. So I'll stop the video here, and I'll see you guys on Thursday.